Hello and welcome to By Excellence Tutorials. I think in the previous videos, I made mention that we are dealing with a series of rotational dynamics questions, tutorial questions. Yeah, so this is, I think, the number 5, the number 5th question of the series. All right. So the question says, the system is released from rest. How fast is the frictionless wheel with that inertia and the radius turning after the 520 gram mass has fallen 2 meters? How long does it take the mass to drop this far? So we are being asked to find the angular velocity here and also the time that it takes that mass to drop. All right, so now the first thing that you have to keep in mind is to know what you are looking for. All right, that will be the first thing. So here we know that in the first question, we are looking for the angular velocity. Now, you get now to dig deeper to say, how do I get my angular velocity? Looking at what I have been given. So you can see that what we have been given is not enough for us just to start calculating for angular velocity there and then, because from this data that we have, we can see that we can only find our angular displacement, of which is s over r, and the s here we've been told that it has fallen how long? 2 meters. So that 2 meters is the same distance which will act like, maybe it's here like that. That will be the S, the 2 meters that is going to cover, more like the arc length. All right. I don't know if you still remember in circular motion where you talked about the arc length and also being equal to the angular displacement times the radius. All right. We're giving the assumption, we're doing the assumption or making the assumption to say the radius is almost equal to the arc length, or the angle, the angular displacement is very small, it's very minimal, such that the radius and the arc length are the same. All right, so you ended up having that. So we can have 2 meters here over 7 centimeter is basically 0.07 meter. So what we get here is 28.57. So 28.57 rads. All right, so we have that. At least we can get that. Now, still, that information is not enough. Since we have that one, we know that we can use this formula to find the angular velocity. How fast? All right. So you can find that too. So you can see that in that equation, we only have initial angular velocity and the angular displacement, which we have just calculated. So we need to know what the angular acceleration is for us to get the angular velocity. Now, how do we go about it? Is to analyze the system that we have here. So now we have this system. Let's say this is mass 2 and this is mass 1. All right. So mass 1 has got that tension. Let's say that is tension 1, and its weight, that is m1g. Mass 2 has got also the weight, that, and also tension 2. All right, so this is like this. All right, so we have that system that looks like that. Now, we get back to Newton's second law of motion. So Newton's second law of motion states that the summation of forces gives you motion. All right, so now you look at the forces that are here. So here we have the tension force and the weight as the forces on this system. So now we are going to get the equations for this Newton's second law for each mass here, mass 1 and mass 2. So let's go for mass 1 first. What is going to happen is that the mass, as mass 2 is going to be dropping, mass 1 is going to be going upwards. So what we expect is T1 minus that weight of mass 1 being equal to the motion, mass times acceleration. So now, what we're going to have, let's make T1 the subject of the formula. So we're going to have plus, because the weight has gone the other side, which it was a negative, it becomes now a what? A positive. So let that be our equation 1. Okay, so let's keep this one. We're going to use it. All right, so now, having done that, we do the same also for the mass 2. So mass 2 is going downwards. So what we have the weight minus the tension. All right, the weight of this mass minus the tension 2 equals. So the tension are not the same. Please, the tension are not the same. So don't make such an assumption. All right, so the weight of mass 2 and minus the tension of mass 2 giving us also motion. So we make T the subject of a formula. We're going to have T2 being equal to the weight minus that. So let that be our equation 2. All right, so we have established from Newton's second law. Now, there is one more thing here. It's not all about only about forces, all right? There is also something to do with torque or the turning effect. The effect of those forces, of those tension on that system. All right, so now we know that torque is given by moment of inertia times angular acceleration. All right, I think we're getting there. So now, notice this, that we have two forces or two tensions here, tension 1 and tension 2. So these two tensions are going to cause the torque, torque 1 and torque 2. Now, we know that torque is given by the force, times the perpendicular distance, of which the perpendicular distance in this case is basically the radius of that wheel. So we have force times R, and this force is tension times R. All right. So now what we're going to have is, since this is going in the direction of mass 2, it's dropping down, it's going to have to be like the torque for tension 2 is greater than the torque for tension 1. So torque 2 minus torque 1 giving us that. All right. Now, look at this. I made mention here to say torque is basically tension times the radius. All right, in this case. So now it means that torque 2 is going to be tension 2 times radius minus this one, tension 1 times radius, is going to be that. And let that be our equation 3. So what do you see here? What you can see is that tension 2, tension 1, we can replace them by these equations. So what are we going to have? We're going to have radius multiplying tension 2, and tension 2 is m2g minus m2 a minus r. Tension 1 is basically m1a plus m1g, all right, equal to inertia times angular acceleration. All right. So we can distribute this, right? So after distributing, what are we going to get? All right, we're going to get something like m2gr minus m2ar, and here we're going to have minus m1ar and minus also m1gr equal to I alpha, like that. Now, we can see that in this equation, we have both the angular acceleration and also the tangential acceleration. So we need to convert one. So we can convert the tangential acceleration. We know from here, let me write here, we know that tangential acceleration is basically r times alpha, or r, the radius, times the angular acceleration. So what we're going to have is that we're going to have, this is going to be written like this, minus m2 a, here it's going to be r times alpha, and then we have r here also, r times alpha, and then we have the r minus m1 gr equal to I alpha, like that. So we have that minus m2 r squared alpha minus m1 r squared alpha, all right, r squared alpha minus m1 gr equal to I alpha. All right. So what we're going to do now is to take everything that has got alpha to one side, and we're going to have, what are we going to have? We're going to have mgr this side minus m1gr equal to I alpha plus m2r squared alpha plus m1r squared alpha, right? So we factor out the alpha here, and and what are we going to have? We're going to have m2gr minus m1gr being equal to alpha I plus m2r squared plus m1r squared. So these are basically initials. So we divide both sides. By that. Okay, so our alpha is basically going to be m2gr minus, okay, so r is also here, r is what? It's common, r and g is, they are common. So I'm going to factor them out. Then I'll say rg is going to be m2 minus m1 over I m r squared plus m1 r squared. So now from here we can get the angular acceleration. So we said that angular acceleration, so our G is 9.81, 9.81, and the radius here is so the radius is 7 centimeter. Okay, so you just write here. Okay. Okay. So the radius here is 0.07, and the mass 2 is 0.52 in kilogram, and this is 0.5 over the moment of inertia that we've been given, 0.005 plus 0.05, sorry, 0.5 the mass here okay. So the mass is 0.52. I'm multiplying by the radius, square of the radius, which is 0.07 squared, plus the mass also 0.5 times the radius 0.07 squared. That. So what will be our alpha? So our alpha is going to be you begin to punch. So let me just pause the video so that I punch this one. So the acceleration is found to be 1.1.337 4 rad per square second. Okay, so now we have also the angular acceleration now, and now I think we'll be able to get the angular speed that we are looking for. Okay, so final angular speed is going to be initial. This system started from rest, so we have 0. Sorry, the equation is supposed to be like that. This, okay. So we have 0 rad per second plus 2 angular acceleration. We've just found that, and the angular displacement, we did find this one, and it was 28.57 rads. Okay, so the final angular speed is going to be 78.514, and we square root both sides. We are going to have the final angular velocity as 8.86 rad per second. So this is going to be the speed that the question is asking us. That's how it will drop, or the speed at which this system will drop. Okay, so now, how long does it take the mass to drop this far? Okay, so now they're asking us to find the time taken. So at least we have a good number of things, and we know that final angular velocity can also be written in this form, so that the time taken is basically that. So now, since we know all these here, we have final is 8.86 rad per second minus 0 rad per second over the angular acceleration, which is 1.374 rad per second. And our time here is going to be 6.45 seconds. So this is how you find this question. I know it was involving and all that, but I believe I explained in at least a simple way that you are able to understand or get the concept behind it. Yeah, so if you have not yet subscribed to the YouTube channel, kindly subscribe, and don't forget to click on the notification bell so that every time I upload new content, you will be among the first people to get notified that there is new content on the channel. Well, and if you've loved the way I've explained and everything, give it a reaction. Give me a reaction. Give it a like, comment. At least comments, they give us feedback so that we can do better next time for you. So thank you so much.